Okay.
Hey,
Hi.
Randall.
Yeah, okay. Hi everyone. Morning. If anyone feels like they want to put on their cameras, feel free to do so. No pressure though, but that's it's great to see people as well too. Anyway, my name is Randall or Randy for short. And thanks a lot to Fazil and Daniel for inviting me to give you a guest lecture today. So to talk about digital audio effects. So one application of digital signal processing. And I thought I'd say a few things first, maybe about where I am, and then I'll tell you about who I am a bit. So right now I'm based in the what's called the Institute of Sound Recording, which is in music and media, and this is in the University of Surrey, just outside of London. So I'm based in the UK right now. I've been here for the past 2 years. Um, and it's an interesting bachelor program, which is so it's called Music and Sound Recording, and it's sort of this unique combination of audio engineering, music, and recording. And so it's really a specialist course on all aspects of audio. And I tend to teach or do research, teach and do research in part of audio signal processing a lot. And many of our graduates go into various audio and music industries. And they've done, really exceptional things. So, they've won Oscars and Grammys, and we've had graduates do the sound for Gravity, all of these kinds of things. And they're all, audio signal processing is sort of a fundamental part of all of these various activities. Um, in our department, we also do a lot of research in what's called psychoacoustic engineering. So, interpreting sounds and understanding how humans hear sounds as well too. We do things about spatial audio when you have sound sources in space, physically in space. So, you've probably seen, very old school ones are sort of 5.1 surround systems, but now you have sort of really big sort of spherical type things to produce sound. And you also have spatial audio and headphones, all these things. And we do a lot of signal processing in audio as well too, which is some of the things I'll share with you. So who am I? I've actually been in your place maybe, I don't know, it's a long time ago. It's probably almost, 20 years ago. I was taking that course. I'm a graduate from the elect program too, so I know exactly where you stand. I've taken this course that you're doing as well too. I also did some studies in the US. I did a master's in acoustics, and then I was in Europe since around 2016. I did a PhD there and a postdoc, and then I moved here in 2023 to the UK. Got a position here as well. I put this up here because if any of you are thinking to do studies abroad outside of Trinidad, feel free to get in touch. I'm more than happy to give you advice on my path and how I was able to, go abroad and do studies. I know that's something that many of you might be interested in doing after your undergrad. So feel free. My email is on the slides. Feel free to get in touch about that. Right? I mean, it's challenging sometimes, but I could give you some good pointers on where to look, depending on what your interests are. Okay. Um, so I'm a lecturer here, and I do research as well in acoustics and digital signal processing. And this is just a slide of a bunch of, various activities I've been involved in over the years. I've worked on, doing what's called sound synthesis, so synthesizing musical instruments, and I've done that with the steel pans recently. I'll put a reference about that. I've worked on something that's called thermoacoustics, which is about converting heat to sound and vice versa. And we develop a sensor on that. Worked on hearing aids, so trying to do the digital signal processing for improving the sound that someone has in their hearing aids. So for instance, people who are hard of hearing, they have these hearing aids which have microphones on them, but they receive information that is, could be someone that you're talking to, but could be a lot of noise in the background as well. So how do you reduce that noise? And these things. So also for hearing aids and for cochlear implants, done that. Um, I've done a lot of work as well on room acoustics, so understanding, and that's a bit of what I'll talk about today. Understanding how sounds propagate in spaces as well. And recently we've done some stuff on bioacoustics, trying to understand how we can localize bioacoustic sounds such as birds and whatnot in space using various microphones. So lots of various topics, all in audio and DSP. So if you're interested in any of these, feel free to reach out to me and we could chat. Sometimes I do or can do collaborative work with undergraduate projects for your final year project as well too. So happy to be involved in that too, if anything interests you. Okay. Okay, so that's enough of me. What are we going to talk about today? So I thought I'd, not make it too heavy, but still kind of interesting at the same time, and also um, tying back to some of the fundamentals that you've learned in this course, and maybe trying to see some things in a few different perspectives as well too, which I think has really made sense to me. I mean, I remember when I was doing this course that you're doing now, and sometimes, things were really abstract. I mean, they would kind of make sense mathematically and sense, but I was having a hard time sometimes connecting the dots, and it took me a long time to do that. So I hope to share some of those perspectives I've learned over the years. So first, I'll talk about impulse responses and convolution, which is a really fundamental concept in being able to develop digital audio effects. And then second part, I'll go into a bit of how we do what's called artificial reverberation. So this is an example of an audio effect, which is understanding of how sounds propagate in spaces and how we can model that through DSP, very fundamental DSP techniques. So using FIR filters or IIR filters. And we'll see two very basic examples of that, and we'll hear what those things sound like. And we'll see how all of these tools that you've been learning, posed on zeros, Z transform, um, all of this sort of stuff, difference equations, how all of these things actually play a role in this. And this has been a topic of research for understanding how sounds propagate in spaces for a long time when people design concert halls and design spaces for listening to music. But recently, there's been sort of a peak or sort of a rise in the interest in this because of virtual reality and augmented reality and all these things where you're now embedded in virtual spaces, and you need to make sure that what you see around you is consistent with the sound in that space. And that can be a really important characteristic for creating what people call immersive experiences and really making these technologies good. So that this topic has actually been on the rise quite a lot. So talk about that, point you to a few bits of literature, but we'll just scratch the surface, right? Just to show you, get a kind of glimpse into how we use these DSP techniques. And then finally, I'll point you to a bunch of other resources for doing other types of digital audio effects and where you can look for that, what you can look for. Okay. All right, so let's get started by looking at impulse responses and convolution. And for this, we're gonna maybe go back to some of the fundamental things that you've learned already, because it's important that I want us to all be on the same page with some of these basic concepts. And the first one is remembering what we talk about, what we mean when we talk about linear time invariant systems, LTI systems. Uh, for me, again, as I keep remembering when I was a student in this course for a long time and throughout elect, everyone is saying LTI systems, LTI systems, LTI systems. And, it would kind of make sense, but there was still something that was not tangible about it that I was like, yeah, well, so what is the point of LTI systems, right? And it took me a while before I really understood why it's so important and that it's really the foundation of a lot of um, signal processing, right? And it's important. So I want to revisit that concept a bit here before going on because it's really important. So what I'm showing here on the left, well, this is essentially a simple block diagram, right? On the left, I have some input. I'm going to denote that x of n. And on the right, I have output y of n from some system here. And this t with this curly brackets, this just represents some sort of transformation. You can think of the simplest transformation is sort of applying a gain, right? So you have x going in, and y is just some gain multiplied by x. And that's a simple result. But here's an illustration of any sort of other type of input to output. Okay, so that's a system, and we're interested. So a system is taking some input, transforming it to some output. But there are particular types of systems which we call LTI systems. And what does that actually mean? So the first word in that LTI is linear. So L for linear. And so what does that actually mean? Mathematically, here's what it looks like on the slides here. So let's say I have two inputs. So I have x1 and x2, and each of them are scaled by some gain a and b. And I add those together and I send them through a linear system. Um, by having a linear system, what this allows me to do, remember my general system is taking this transformation of my input. So I'm doing some transformation on this input here, which is what we call a scaled combination, or what we call a linear combination of inputs here. And basically what I can do is I can take this gain A and I can take it out of the transformation. I take the B out of the transformation, and I can, instead of having this transformation acting on the sum of these signals, I could decompose that into two sums. So one, which is A times the transformation on x1 plus B times the transformation on x2. And if I represent the transformation of x1 as y1 as sort of the output of the system due to input x1, and y2 as the output due to input x2, then I simply write it as such here. So basically all this is saying is that this, instead of this transformation or the output acting on this entire sum here, I could sort of decouple that into two separate outputs here. The sum of these two separate outputs that are scaled by A and B here. Okay, so that's essentially what a linear system does. And time invariant, which is probably a bit easier to understand here. So for time invariance, what this means is that the signal is no matter so you have an input here, x of n, and our output y of n here. And so time invariant one is where no matter if you shift the input at any particular time, the output always remains the same, right? So for instance, if I were to delay this signal x of n by some amount, then the output is also delayed by that same amount. So the system always has a fixed behavior over time. No matter when you apply this input on the system, you're always going to have the same output. So here's an example for if I delay a system by two samples. So on the top here, I have x of n, it goes to the system. I get some y of n output here. If I delay x by two samples here, right? So you see I have these two 0 points here. The input here is simply delayed. And my output is just simply, it's the exact same output as before, but it's just simply delayed. So time invariance, right? The word tells you what's going on. So the system is invariant to changes on the input, right? If that input just happens at a later time, the output will be exactly the same happen at a later time as well too. Now, when thinking about time invariance, you probably think, well, yeah, but all systems probably, if I think of an electrical circuit or something like that, it's probably time varying because, over time the tolerance of resistors change, the capacitors are not as great as they were before. And so the output is actually varying a bit. But usually for when we look at modeling systems and we want to model it as time invariant system, we consider sort of a particular period of time for which, over, let's say, over a year, let's say, for instance, a system is probably going to be time invariant, like an electrical circuit. We don't expect any big changes here. And so that's an important modeling criteria that we can introduce here. Okay. So essentially, linear time invariant systems, they combine these two properties. They combine this linearity and this time invariance. So now if I have some input, which is right, some scaled or delayed input here, so this n minus k, where k represents that sort of delay step here, plus b times x2, n minus p, p represents some other number to be a delay. The output is just simply A times sort of this y1 of n minus k plus b times y2 n minus b here. So what it means is that, again, I've used these properties of linearity to decouple this sort of transformation on the top here into these two separate sums. And even if the input was delayed by some amount k and p here, each of these, the output is the same, but it's just delayed by that corresponding amount. Okay. And so that's what essentially a linear time invariant system is. And you could think about this, in a really simple way. Imagine you have an input here. X1 is probably like a vocal or someone singing, and X2 is someone playing a guitar. And A and B are simply gains on each of these two. The output is simply that same gain A multiplied by the output of the system of that vocal alone, plus B times the output of that guitar alone, um, due to X2 here. So that's all linear time invariant systems are. And these are like I said, they're really important because they're fundamental building blocks for the way in which we can model audio systems and the way that we can start to design audio effects and all of these things. And so to start to understand that, we need to look at another particular function, which is something that's called the unit impulse. So the unit impulse function, it looks as follows here. So it's denoted by this symbol delta. And so sometimes we in fact call discrete time unit impulse delta function. And so only if n is equal to 0, I have a 1 here. And for all other values of n, so n here is essentially a sample number, is 0. So for all time, I just have 0, and then except at n equals 0, I have a 1 here, and then it goes down, right? I mean, it makes sense that this looks like why we would call this an impulse, right? It's one particular value at one particular time, has an amplitude of 1, and that's what we call a unit impulse. Now, if we want to look at particular systems and we want to understand their behavior, what we can look at is something that's called the impulse response. So the impulse response is the output of any system in response to a unit input signal. So what do you mean by that? So unit impulse signal, right? This delta function, this delta, right, which is a value of 1 at n equals 0, 0 elsewhere. We apply that to a system and we get some output. That output is what we call our impulse response of that system. And it is a fairly fairly simple basic idea, right? You apply this to your system, you get some string of values, that's your system output. Why is that important? Well, it turns out that for linear time invariant systems, um, if you know the impulse response, you can essentially compute the output of the system for any input signal using a convolution. So that means is that linear time invariant systems are uniquely characterized by the impulse response. So I mean, it's a really a profound message here because it says, look, I just have this one sort of this one piece of information, which is, I have some system, send it with an impulse, I hit it with an impulse on the input, I get some output, and that impulse response, if I have that information, I can predict the output to this system for any input, but only for LTI systems. And that's where LTI systems become really important, right? Because that's why we use LTI systems, because we can do something like this. And the way that we do this is through what's called a convolution, and I'm sure that's something that you've all seen quite a lot. But I'm gonna this is a really big point, and it's hard to digest to just believe it. So let's kind of see why this might be the case. Okay. Let's look at a really simple example. So this is a bit of a different way to look at convolution. So let's say I have some input signal here. So I have some input signal here, really simple input signal, has 0 0.8, 1.8, 1.2, 0, and 0. And that's my input signal, and this is my impulse response. Let's say, I did some measurement on my system and I was able to obtain an impulse response. And I want to be able to convolve these two signals. Well, one way to look at this is that you can actually decompose this input into the following. So you can actually look at an input, a string of input values as a series of impulse functions or impulses or delta functions, as we call them, but they're going to all be scaled and delayed. So for instance, I can write this first sample here, zero point 0.8. I can write that as zero point 0.8 times delta n. And remember what, if I go back a bit, remember what our definition for delta n was. Delta n only had a value of 1 if n is equal to 0 and 0 elsewhere. So I can perfectly represent that first sample of my input signal as just a scale delta function. It's simply zero point 0.8 times delta n. Fine. The next sample, I can actually represent that now by also a scale version of a delta function. So now I have 1.8, but it's in fact delayed by one sample. And this makes sense, because if I were to substitute n is equal to 1 here, that would correspond to delta 0. And we know delta of 0 is equal to 1, and that's a value of 1.8. And we could do the same thing for the other sample. So 1.2, that has also a scale delta function. It's scaled by 1.2, but delayed by two samples here. And if I add all of these signals here on the right-hand side, I get back my input signal. Because remember, for each of these sort of what I call decomposed impulses of my input, remember, it only has a value at one particular, a non-zero value, in this case, at one particular value of n. So here, for n is equal to 0, that's zero point 0.8, and for here n equal 1, that's 1.8, n equal 2, 1.2, etc. So if I add these up, I get back my input signal. So this is the first important point, is to be able to, if I look at signals in general, discrete time signals, another way to think of them is sort of as a sum of scaled, shifted impulses, right? And that's a really important realization when you start to think about discrete time signals like that. And, you know, basically what you do now is that, so actually, first of all, just to say mathematically, you would represent this as follows, right? I can say x of n is equal to summation from k is equal to minus infinity to infinity, and I have x of k multiplied by delta n minus k. So this is just basically how we can write, each of these terms here. You can substitute the values of k, and you can see each of these terms would correspond to one of these terms here. So I can write x of n as a sum scaled shifted impulses, where the scaling is given by this particular value of x of k, and k here also tells you the value of the shift. Okay. Now, what you can think about now is, well, look, if each of these if my input signal can be decomposed as a sum of scaled and shifted impulses, then essentially each of these gives me some type of scaled or shifted impulse response. Because remember, I told you that if we go back here, I told you that if I have an impulse and I send an impulse to the system, I get an impulse response h of n. Now, because we have linear time invariant systems, it means that I already know the output to delta n. The output to delta n was h of n, but this is just simply scaled now, and that's that scaling factor. So I can just simply multiply zero point 0.8 by h of n. And we know that the systems are also time invariant. So even if I were to delay that impulse by some sample one, then the impulse response h of n would just happen at one sample later. So as you see here, but it's also scaled in this case, right? And then you also have the same thing for n minus 2 here. So the impulse happens at some time later. So you also have your impulse response happening at some time later, n minus 2, but then it's also scaled on top here. And we're able to do this because our system is linear and time invariant, right? So if we just sort of recap for a second what we've done, right? We've taken an input signal, we've thought of it now as a sum of scale and shifted impulses, but each of these impulses now produces some scaled and shifted impulse response, right? Because we have this information h of n already. This is all the information we need because this is just simply shifted version of h of n and h of n minus 2 and just scaled. And in fact, if we add that all up, you get your output y of n here. And now if you look at this mathematically, what's happening, so if you look, if basically I'm summing all of these scale and shifted impulse responses up, right? And if I look at the particular samples at the various values of n, so for n is equal to 0, it's basically adding up this sample here, and this sample here. And I can write that out mathematically as follows here. So, this first one is 0.8 times h of 0, which is this one. This next one is 0.8 times h of 0 minus 1, because here, remember, n is equal to 0. And then on this point here, it's 1.2 times h of 0 minus 2. And I could simply write that as, if I recognize, in fact, that 0.8 is, in fact, x of 0, because it's this first value here of x. This 1.8 is x of 1, so that's that second value of x. And x2 is 1.2 here. So this is x0, h0, plus x1, h minus 1, plus x2, h minus 2. This is just writing what we see visually in terms of indices here. And you can continue this process for different values of n. So if n is equal to 1, you look at these set of samples that are at index 1, and then you add them all up. And if you go through the indices, you'll see you end up in a similar place, right? Basically substitute n is equal to 1 here. And so now these indices of h changes, right? So it goes from h1, h0, and h minus 1. But they're still scaled by x0, x1, and x2. And I continue going again for y of 2, and I do the summation, and you see sort of this pattern occurring here, right? The same pattern. x0, x1, and x2 are the same, but the values of h are changing. And h is my impulse response. Remember, I have that information already. Okay. And you could keep going, and you will see the pattern develop. And eventually, what you get to, if you write this in a more general form, what this corresponds to is, in fact, the discrete time convolution, right? So this is essentially what that discrete time convolution is. It's x of k multiplied by h of n minus k, and that's a summation over k from minus infinity to infinity, where k is just this index that's shifting here, right? So this is probably what you've seen already, right? This is in general what a convolution looks like, and in here I'm specifically talking about y of n. The output of our system is essentially a discrete time convolution with our input and our impulse response H of n of the system. And I can write that in a shorthand notation with this sort of star that you've probably seen already, right? So the important point here was to show you that, because we're considering systems that are linear and time invariant, we can uniquely characterize them by what's called the impulse responses. So sending an input with a unit impulse and getting an output, and that's our impulse response. And then once we have this impulse response, we could basically we could essentially synthesize the output of the system for any input once I have that once I have that impulse response, and I do that through a discrete time convolution. And that was because we were able to view our signals, our input signals, or signals in general, as sort of being decomposed as a sum of scaled and shifted impulses. Okay. And that's how you essentially, that's another way to look at how you will get to a convolution, or a discrete time convolution in this case here. Okay. And that's sort of the core. That's what we're going to use. I mean, it's one way in which we design basic types of audio effects here. Okay. Maybe I can ask if there are any questions at this point, right? That was sort of the sort of fundamental parts before I'm now going to a bit into the application. So I just wanted to ask if there are any questions, if we're good, or thoughts or questions. Oops. Anyone?
Some of
I
this
know.
is things that they would have done early on in the first sort of quarter, the first few weeks of the semester. And
Perfect.
we did
Good.
it a number of times since. It would be nice to hear if they remember any of this, or if
Okay.
anybody has any questions on it.
Okay, people could also give like a thumbs up or anything like that, just so I know that yeah,
Yeah,
everything is going good, right? Which I assume.
we
Okay.
got a couple no questions in the chat. Just thank you
Oh,
for
we have.
saying that there's no questions and good so
Oh,
far.
okay, great, fantastic.
Yeah,
Okay, I didn't see the chat. Okay, great,
yeah.
great, good. All right, good. All right, so that was really, I really just wanted to make sure we were all on the same page before getting into more of the. Now we'll jump into a bit of the audio effects and look at some basic ones and how we use these concepts or these ideas to design audio effects for artificial reverberation, what I call artificial reverberation. So, you know, like I was saying, artificial or what's called artificial reverberation is essentially trying to simulate the sounds of rooms. So when we talk, you probably notice already when you talk and you go into different rooms and different spaces, things sound differently, right? If you go in a church or something like that, it sounds different from if you're in your bedroom or if you're in a classroom. I remember in when I was a student there, I don't know, some classrooms were actually terrible and they didn't sound very good. I don't know if that's changed now. But right, you probably noticed this. And um, like I said, in terms of application, this has become really a growing field ever since, introduction of or more interest in virtual reality, augmented reality, all of these kinds of things. So virtual reality, when you have simulated spaces that you're in, you also want to simulate the acoustics of that space because that's gonna, you need to have sort of consistency between, the physical space that you see and what you hear, right? And there can actually be a disconnect because some people it's already been found that, some people when they see a certain space, they expect a particular type of sound. And if there's a mismatch, that becomes really problematic for designing these types of experiences. This has also been used in, the design of, concert halls, theaters, or practice rooms, any of these kinds of things, being able to sort of predict what the sound of a space would be before you build it is sort of a really important task as well too. And being able to, you know, sort of what there's a word that's used which is called an oralization, which is allowing you to walk through a simulated space before it's built and get an idea of how it sound. Um, and I'm just going to talk about some basic models on how that is done. And essentially, it's done by the first thing that you do is that you consider the room as a discrete linear time invariant system. So between any sound source and any receiver, so if I'm talking and you're listening, or I have a microphone that's recording in the room, or maybe it's your smartphone that has a microphone, the path between, so my voice acts as the input and the microphone or the receiver on the other end acts as the output. Everything in between that, we can model it as a linear time invariant system. And that's really important because if we impose that model, what it means is that if we have the impulse response of that linear time invariant system, then we can actually synthesize or simulate any of the acoustics in the room from that position to the microphone position. And so for room acoustics, so understanding sounds in physical spaces, the particular the impulse response is referred to as a room impulse response, so an RIR. So that's a common terminology that you'll see pop up in the literature. So have a look at that. Yeah, you'll see that, and I'll use this term throughout. So that's one of the fundamental ingredients of it's actually what a lot of models are trying to build, because they're trying to simulate how do I get the impulse response of a room? Because once I have the impulse response of the room, I can synthesize the output with a convolution. That's essentially what people are doing. Um, right? So right, and these impulse responses of rooms, or room impulse responses, um, they can be modeled as finite impulse response filters or infinite impulse response filters. And we'll see two examples of that, right? So it's FIR and IR filters, which you've seen before, right? So again, the point is modeling the sound of the space really involves obtaining the room impulse response between any source receiver pair within that space here. So here's an example, for instance. So let's say I have a dry sound here, which I'm going to play. Should be able to hear that, right? Right?
Yeah,
And
definitely heard it.
okay, and then if I had the room impulse response of, for instance, I had one of this particular space here, and I wanted to sort of synthesize what that drum sound would sound like in this space, I can simply use that room impulse response and do a convolution, and then I could get something like this. Right? So I hope you hear there's some kind of difference. It sounds a bit of what we call reverberation, which I'll explain. It sounds a bit different. People use the word artificial reverberation when they're referring to, sort of you can come up with any sort of random space, a non-physical space, and that probably has a unique sound or an interesting sound that people want to use for creative purposes, if they want to use this kind of reverberation for music production or these kinds of things too, right? So there are different goals in this area. So some people try to really model existing rooms very accurately. Some people might do it from a more creative point of view, and they want to synthesize sounds in odd spaces or strange spaces. But this is sort of the thing that people would want to do in the end. But let's talk a bit about the physics or model of how we would think about an impulse response or a room impulse response being generated. So what I want you to focus on is an animation that I made. So on the top left-hand corner here there's a sound source, which is denoted by this black dot, and there's a small orange circle, which is a receiver. And what I'm going to do is I'm going to send a unit impulse from this sound source, and then you're going to see what happens on the receiver. Now, this room here, this is sort of a top view of a room, and these walls here are just represented as, rigid surfaces. So surfaces where there'll be reflections. So when you make a sound, it reflects off one wall, comes back, it reflects off the other one, it comes back, and there's lots of reflections that happen over time, right? And what I'm going to show you at the bottom here on this graph here, this is how the room impulse response is going to be generated based on these reflections. So this is what the microphone sees, right? And the microphone is going to see sort of this impulse response. And ignore the top right hand for now. I'm going to explain that after, right? But just have a look at how this is, and we can see we can now start to make connections between some of these theoretical things and more practical things. So for instance here, so if I play this, so you see I've sent out what we call a spherical wave from that sound source. So basically, you can think of it that this circle here, that's your impulse. So all along that value, you can think of it as, that's a value of 1, but for all of the time, there's no sound emitting from there. So I've just emitted an impulse, right? And if I look at this impulse, you see, it hits the wall here on the top, but there's a reflection, which is denoted by this green. And as soon as this initial sound from that sound source reaches the microphone, see there, I have a peak here in my impulse response. So that's the first peak that I see. And if I run the animation, I see reflections happening all over the space over time. But the reflections actually slowly die out over time, which is why they become lighter in color. Sorry, yeah, lighter in color on the top left animation, and they become smaller in amplitude. But so it starts with this initial sound that hits the microphone, which is denoted by this main peak here. And then there are a few other peaks, and then over time, there are a bunch of these other small little peaks here that are coming up here, and that's what's creating a room impulse response. So this is essentially an impulse response of an LTI system, but the LTI system here is my room. Okay. And so we can look at that again. Right? You see the reflections there, and every time one of these waves touches or hits the microphone, it pops up. It registers on the microphone with a different delay, and a different amplitude according to it. So essentially, I can take this room impulse response and I can convolve it with my input signal, and then, that's sort of a synthesis of what sound would sound like at that particular receiver position here, right? And that's all through discrete time convolution. Now, there are particular methods which I would not go into in this talk, which is about how do you actually measure um, such an impulse response, right? You can do this through a bunch of different techniques, and you can actually, that's something that people do as well, to try and get impulse responses from different source receiver positions. On the top right, where you might be wondering, this sort of funky looking picture here. This is actually so on the top left here, I should say, this is what sort of physically happens in terms of acoustics. But from a signal processing point of view, we need to model how these physical processes happen. And so one particular model is what's called the image source model. And so this model theorizes that, well, in fact, you can think about, instead of thinking about the sound bouncing about from different reflections, or having reflections from different walls, I can actually consider alternatively that this impulse response is generated by, this is my initial sound by this black dot, and a bunch of what we call image sources or ghost sources. And these image sources, they're positioned in a particular way that, the time it takes for the sound to arrive corresponds for the time it takes for a particular reflection to arrive at the microphone here. And they're also scaled accordingly with amplitude. So this is an example on the right-hand side of what we call the image source model. And so I kind of wanted to see, well, okay, how does this actually work? And what that might look like. So a model which we can think about generating this impulse response is due from all of these tons of other sources. And uh, there's there's a lot more to be said about that, and you can actually model. I mean, with having that sort of abstraction, you can actually model this simply with a finite impulse response filter. But I'm not going to go through that in detail. I'm going to show you from a much simpler example that you can then extend to this here. Okay. Um, so that's what a room impulse response for rooms, impulse response for rooms look like. And we need to have some interpretation of what this impulse response means, or room impulse response means. So that first peak, or that first sort of initial peak that we see, that occurs at some time delay t0, and that's the time it takes for the sound to arrive to the receiver directly from the source. So that's a straight what we call the line of sight from the source directly to the receiver. And that's what we call the direct component. That usually has the largest amplitude. Then after that, we have what's called early reflections. So we have sort of main reflections from a wall or from a ceiling or from the floor. And these are sparse. So meaning that, they're not very compact and densely located, but they occur at, sort of sparse intervals in time here. And that's really important for a particular sound of a room. And then after those, we have what's called the late reverberation. So that's where, this word reverberation comes into, because after some time, the sound is bouncing all over the room and it becomes really dense and sort of what we call diffuse, because there are many reflections that are happening all over the space. They're happening at an exponentially decaying amplitude here. And that really is something that characterizes a particular space as well, too, right? It gives unique characteristics for sound. So that's what we call no late reverberation. And this is sort of, the basics of how people start to think about modeling the acoustics of spaces. And so creating computer models from room impulse responses essentially is one of the areas where people are looking into, which is called artificial reverberation. And it's really predicated on DSP concepts. And I'm going to show you a couple of examples on that. But there are really tons of methods out there on how to do this. But I wanted to give you sort of you know, sort of a glimpse, I guess, into this field and what people are thinking about out there. And there's a lot of engineering decisions that people need to make. They either need to, there's trade-offs between, how physically accurate this is. One thing that we do here at the University of Surrey is, not necessarily consider how accurate it is, but how perceptually relevant it is. So it turns out that you can get away by not having to model in detail many of the physical aspects once it sounds right, or it sounds what we call plausible, realistic, then then you're good to go. So we try to understand what are the characteristics of these things that make it sound relevant, or make it sound perceptually relevant, I should say. And this is interesting too, because, not only can you synthesize reverberation, but you can do what's called de-reverberation. So you can actually use these same modeling techniques to model certain signals and spaces and come up with ways of using DSP as to how to remove that late reverberation from signal, how to de-reverberate signals. And there's a lot of work on that. So I've pointed you to a couple of references here, which I think I mean, again, there are tons of references, but these are actually two really good overview papers if you're interested in this field. And within that, there are tons and tons of references that you could look at. But I think these two are, if you're kind of getting into it and you're interested in this, those are two good places to look at here. Okay, so what I want to show for the remainder of the lecture is sort of two very simple models of how we can do artificial reverberation. And this is actually, you know, where things got started with this. When people were doing this in the 50s or the 60s, they were trying to figure out this problem and how do we synthesize that? And it turns out, you can get a lot of interesting things by some very simple models. But it's sort of the foundations that I thought I'd give you and show you where, some of the DSP core techniques are relevant. So I'm going to go through that. So maybe I'll stop here again and ask if there are any questions, particularly about this before I go into the more DSP-ish stuff.
And
No.
just like before, if you don't have questions, it'll be helpful to just indicate that you don't have questions as opposed to I've fallen asleep at my keyboard and I don't know what's going on. So,
Yeah, right.
uh,
Okay. Okay,
Virendra
yeah.
was going to ask about how do you know when a signal is acceptably processed, but then you said it's almost right after he thought
Yeah.
about the question.
Yeah. I mean, yeah, Virendra, this is a really I mean it's a tough question. And it is a good research question because people argue for, oh no, it's not physically accurate. You've left out a lot of things, but then other people say, yeah, but doesn't matter if you model um, this very specific thing. At the end, it doesn't really matter if it's not perceptually relevant. But it depends on your end goals. If you're perfectly happy with, designing a system and saying, well, yeah, it sounds good. It sounds realistic to me, then, you can probably get away from that. The other part to that is that there's trade-offs inherently behind this for computational complexity, right? You can imagine that if you wanna physically model everything like really accurately, it's gonna take you a lot of resources computationally. Whereas, the more stuff you get to leave out, the lighter it would be on your system too. So it's also, this trade-off between physical and perceptual relevance also translates to trade-offs in computational complexity and accuracy, right? So it's a very live debate, I would say. And yeah, it's a good question. Cool. All
Uh,
right.
I don't think
Good.
we have any other questions,
All
so
right, cool. So,
okay.
okay, I'll continue, if that's all right. Yeah. Okay. So, you know, we really need to start somewhere, right? I mean, we've seen that it can be a really complex problem, already. There's a lot to think about, but I want to start from, a really basic, place, which still has interesting results and would probably help you link, these DSP concepts to something physical. So let's think about this really simple scenario, right? Got two people talking in a savanna here, a big open space, in Queen's Park, Savannah, wherever, and they're just talking, right? So what's physically happening, right? Well, if person A, so I'm going to use these letters here that refer to the different positions. So person A talks to person B. Now there's some time, and I'm going to denote that as T1, and T1 milliseconds or whatever units you want to use, that it takes for the sound to arrive from A to B. So, the person B hears the sound sometime after A. And I mean, you can calculate that time because we know the speed of sound. The speed of sound is something like 343 meters per second. And if we know the speed of sound and we know how far apart A and B are, we could do a simple computation to figure out how much time it took from the sound to arrive from A to B. So that's what we call the direct path, right? It directly goes on the line of sight from point A to point B, and we denote that by T1. But there's also another path where the sound travels, and that's a single reflected path. So the sound also travels from A to G to B, and it takes a time, so it takes some time T2 to go from A to G, and then sometime T3 from G to B, right? And then this time, so the sum of T2 and T3 should be greater than T1 because it's a longer distance that you have to travel going from A to G to B as opposed from A to B directly. So the sound that arrives at B is consists of two components. One that's sort of this direct component and one that's delayed a bit, right? Due to this reflecting path here. Okay. Um, And mathematically, we can start to represent that or look at this as follows here. So let's think again in terms of impulse responses. So let's say at point A here, I had an impulse response x of t, and then this is just some delta function. What's gonna appear at the output at B here, it's gonna be I'm gonna see two peaks, right? I'm gonna see one that's been delayed by some time t1, and I denote that as x of t minus t1. And then the other one that's going to be delayed by some time t2 plus t3. And I'm just simply going to write that as t minus t2 plus t3. Okay, so that's mathematically how we represent the process here. Okay, so we can do a sort of mathematical trick a bit here. We can rewrite things a bit in another way that's a little bit more convenient for us and for developing the system that we want to. So in this case here, what we're showing is that we have, right, the same signal x of t minus t1, and I had x of t minus t2 plus t3. Now I can rewrite this by simply writing, I can rewrite this as x of t minus t1 minus, and then I have in brackets all here, T2 plus T3 minus T1. If I were to add that up, I would get back the same signal here. Basically, what this means is that I want to think about, instead of that delay T2 plus T3, I want to think about a particular delay tau, which represents the delay between this first peak here and this second peak here. So I'm going to denote that T2 plus T3 minus T1, right? Because remember, T2 plus T3 was the time it take from the initial sound to this second peak. But I'm just going to subtract T1 from that. And so that new variable tau, this time delay, is going to be relative with respect to that direct path. Okay, and that's going to be really useful for us in terms of our notation. And so what I have essentially here is x of t minus t1 plus x of t minus t1 minus tau here. Okay. And there's one more sort of mathematical trick we can do is, so instead of considering things as your starting point from zero here, we make our starting point from t1 here. So essentially what we do is we essentially replace x of t minus t1 with x of t. So now how we want to represent the output of our system, some output x of t as just being just corresponding to this first peak here, and x of t minus tau as a second peak with respect to that first one. And the interpretation of this is just, instead of thinking about the direct path from A to B, we consider here x of t to be already at that point B here, right? That's just a sort of rewriting of things to express our output in terms of these two peaks here, where the first one is x of t and the second one is some x of t minus tau, where tau is a delay with respect to that first one. Okay. But the thing is, so what I've done here so far is I've considered things in time in seconds, right? Because we're talking about speed of sound, distances, all these things, but we're in discrete time. Okay, we're in DSP, so we gotta convert this time to discrete values to some samples, right? And we do that by a process of sampling, which I'm sure you've all seen already. And so you've done basically the way that you do this is that you replace this variable t, this time variable t, with some index n multiplied by ts, where ts is your sampling period, ts is equal to 1 over fs, which is your sampling frequency. And n here is the sample index. And that's, we basically replace t with n times ts. That's sort of the standard way to do it. So instead of t, we now have x of n. So you leave out the t subscript s as that's constant, and that's just, cluttering the notation. And then we can represent the delay in terms of number of samples. And number of samples is capital N, which is equal to tau, this time delay. Remember, tau is that delay from the first peak to the second peak, and we just simply multiply that by the sampling frequency, and then we would have the number of samples of delay. So essentially, we can convert, right? Just through sampling, we can convert our continuous time system to discrete time system. So now we consider the output as x of n plus x of n minus capital N, where capital N is the total number of samples here. Now, so that's how we're getting to our discrete time systems, but there's a problem which I'm not gonna address here, but I actually want you, I mean, I want you to think, does anyone see already sort of a limitation of such an approach of considering capital N, the number of samples of delay, as tau times fs? I mean, what problems are you already running into here? Does anyone have any thoughts on that? No wrong answers, just, thoughts to see if anyone's listening.
And you could either unmute and just yap away
Yeah,
or type in
absolutely.
chat. Either work.
Yeah, for sure. I mean, yeah.
Okay.
Yeah, a big number means long delay. Yeah, that's true. But that's not necessarily a problem. We can handle long delays. Um, what about the fact that n needs to be an integer? I can remain quiet too, right? So
I could
no.
also pick on people.
Right? I mean, the fact that n needs to be an integer because we're talking about samples here. I mean, what problem? Remember, we're converting some samples, some delay in time, which is tau, to capital N, which is a delay in samples. So what limitation do you think you have here already?
I guess they haven't reviewed the lectures on sampling and discrete time on.
Okay, the thing is here, I mean, the point is that n needs to be an integer value, right? N needs to be, 1, 2, 3, 4, 5, whatever. But if you have tau times fs, right? What you're gonna get in most cases, sometimes, depending on the values that you choose, you're not gonna get an integer value. So sometimes you need to round or you need to floor that value in order to make n an actual integer value. And so that becomes a
Somebody
bit of
just
a
put in the
limitation.
chat.
Sorry?
Somebody
Uh,
just put that in the chat.
okay. Yeah, exactly. Fantastic. Yeah. Thanks, Kyle. That's great. Yeah, exactly. And that's a problem that you're going to encounter in practice, right? That you would want to replicate a specific delay in time, but then you're limited here by sort of the DSP mechanics of everything that you need to somehow do some truncation or some rounding or something like that. And these are, you know, although very subtle, is a really practical thing because then, for designing audio effects, you can then ask the question, well, how perceptually relevant is the sound if I were to round or the values, if I were to use a different sampling frequency, if I were to, what values of tau actually are perceptually relevant or perceptually meaningful, right? So that's just to give you an insight into, some very fundamental or basic things when we're trying to convert the physics or the actual physical system into a DSP system. There are engineering choices that we have to make because, we're dealing with integers and we're dealing with, fixed sample frequencies and dealing with all of these things that try to convert continuous time variables to discrete time variables. And that has an impact, especially in terms of sound, on sort of the quality, on sort of distortions, all of these things. And through doing things like listening tests and stuff like that, we could quantify perceptual relevance. So that goes back to the other question in how do we assess these systems? So that's some of the things that we do. So anyways, that's a minor, well, it's not a minor point, but it is a point to think about when you're designing these kinds of systems. Okay. So anyways, so that's very, very basic our system here. The output is x of n plus x of n minus capital N, which consists of the direct path plus some delayed version of that. And so the question is, what's your LTI system model for that scenario? Okay, and this is where the whole mechanics of DSP audio design and stuff comes into play, right? You physically know what's happening, and then you want to ask yourself, okay, what kind of digital signal processing structures can I use in order to sort of replicate that output behavior? That's where we started to apply our DSP knowledge and our techniques. Now, the first one I'm going to mention is what we call a feed-forward comb filter. And so it's really simple structure. Couldn't get more basic than this. And it basically consists of two paths. So x of n is my input and y of n is my output. And I can see that y of n consists of two parts. So one, which is exactly that sort of direct path from x of n to y of n. So one of those things are going to be x of n. But then this other part on the bottom, this here is what we call a delay line. And a delay line, we represent that by z to the power of minus n. And so you might know that from your Z transform stuff. And this value, capital N here, tells you the number of samples by which to delay x. Okay, and I'll show you how to program that. So that tells you how many samples to delay x by. And then I multiply by some gain g. And this gain g could be a value from 0 to 1. And we use that value of gain g because, when the sound hits the ground, there's probably some kind of absorption or something in the ground, depending on, if it's muddy, if it's, it's a hard concrete floor or something like that. The sound can be absorbed at different quantities before it reaches the receiver. And so this G allows you to sort of modify that a bit, right? And so for this particular effect, what's interesting is that, if the delay is larger than, say, 100 milliseconds, the effect actually is perceived as an echo. And for smaller delays, it's perceived as a filtering effect. So this ties back into how the design of these kind of digital audio effects from a DSP point of view leads us to perceptual questions as well too, which is really interesting. But let's analyze this a little bit using some of the techniques that we know. So difference equation, I'm sure you've seen this quite a lot, right? The difference equation is pretty simple, right? It's just simply x of n plus g of x of n minus n, because this delay line here, the set of n, this introduces some delay capital N here, and I multiply by a gain here. So it couldn't get simpler than that. The other question you can ask yourself is, what's the impulse response of this system? Remember, again, this ties back to if we know the impulse response of our LTI system, then we're able to simulate any output or synthesize any output due to any input. So the impulse response is simple. We just simply replace x of n by delta n. And you can do this by hand. And because remember, delta n is simply 1 for n is equal to 0 and 0 for all of the time. And it's simply going to end up being delta n, which is the main impulse. And then that same impulse delayed by n samples multiplied by some gain here. And all I've done here is simply replace x of n with delta n. That's how you come to this equation here. And that's the impulse response. And so what does that look like? So here's an example of the impulse response for n is equal to 200 and g is equal to 0.5. Remember, g is the gain that's applied to this delayed path. Okay, and so that's the impulse response. I mean, it's nothing really fancy. It's a main impulse and then the impulse delayed by 200 samples. And so we can do the convolution of some input signal with this to sort of synthesize what the sound is going to be like. And we can ask ourselves the questions, I've got impulse response from the system, so what's some output going to sound like to any input that I feed into the system? And I can put anything, I can put speech, I can put music, whatever you want. How is that sound also going to change as I change the delay N and as I change the gain G? These are questions that you can start to ask yourself. And then you can start to go into computer programming to understand what's happening. And I'll show you that in a second. But just want to say to make a further or to get some more mathematical insight into those questions, you rely on all of the tools that you've learned in this course, So one, you have got the difference equation. I can transform that. I can use a Z transform and transform this. It's pretty simple, right? I mean, y of z is equal to x of z plus g times z to the power of minus n times x of z, right? So that delay is just represented by z to the power of minus n. Um, I can rewrite the transfer function, and so I've got the transfer function is 1 plus, just rearrange for x, y over x, and I have 1 plus g times z to the power of minus n. And then I can look at the frequency response of the system. So if I replace z with e to the j omega ts, so omega here is a frequency, the angular frequency, and ts is the sampling period. If I substitute that for z, what this allows me to do is to plug in values for any omega here and take the magnitude, for instance, of this transfer function, and I can see, from the frequency point of view, what's probably happening to the sounds here, right? So how about we actually look at that? So here's what I do to kind of make sense of, I mean, it's become sort of really rudimentary for me now to make sense of anything. I go to Python and I use Jupyter notebooks. So I don't know if you've all used Jupyter notebooks, but I've uploaded, well, I sent this to Fazil for all of you to have a look at. Um, and it allows you, I mean, it's like a
I
digital
put
notebook.
the zip file in on the course page as well, so they can do it.
Perfect.
Yeah.
Sounds good. And it is a way for you to, it's like a digital lab book where so I've written some of the basics on the theory here, exactly what we talked about a bit here. And then there's a code where I actually build this for you. And you can and I do I'll show you there are some interactive plots here, which allows you to change certain things. So I'm not going to go through too much in the details of the code. Basically, there are a couple of functions that and I'll leave you to go look into this. And so one of them is called so this package called signal in Python, and it allows you to do what's called L filter. And L filters, it does a linear filtering. And you just need to use sort of the coefficients of the filter to do that. And so you develop the coefficients here. Faisal, have you done filter structures sort of as this form here, this numerator and denominator form here? Has this been done? Is this familiar? Anyone?
Yes, they should have done
Yep.
that. We went through all of that over the
Perfect.
last couple of weeks.
Good. Okay, great. So essentially I have B and A coefficients. Now in the filter I just showed you just now, that feed forward comb filter, all of the A coefficients are in fact zero. Because if we look at it here, right? If I look at this transfer function here, it only has numerator coefficients, no denominator coefficients. And then that allows me to basically build my filter here, that I have, I have the first value of B as 1, I have the last value as G, and then yeah, the denominator is 1. So basically what I'm doing is, if you look back at this filter structure here, right? This essentially corresponds to, depending on the value of this delay, depends on how many coefficients that you have in this filter here, which is simply finite impulse response filter. So the first coefficient is going to be 1, and then you're going to put zeros to delay all of the signals up until some value of n. And then that last value is going to have just a gain on G there. And so that's essentially what I've done here. And so it's more instructive to look at this. So what I've done here, what I'm plotting here is the number of samples and the amplitude on the top here. And what I can do here is I can change this value of n. Maybe I'll put this down first. I can change, oops, this value of n here. Oops. Okay, let me do this here. I could change this value of n here. So this value of n, essentially, that's that delayed path. So this is my initial input, and then this is the delayed value. And I could scale that accordingly to some value g. And if I look at the frequency, the magnitude response from this filter, you see something really interesting, right? So if I don't have any delay, the magnitude response looks fairly flat. There's a bit of a roll off to the end. But as I increase this delay, there's essentially what you see as sort of a comb-like filtering effect. So what's going on is that, the main sound that travels from path A to B is interacting with that reflected sound, and you're having, this sort of constructive and destructive interference. So that's why you have kind of these valleys and these dips over and over. And the degree to which that sort of dipping happens depends on this delay. So we could see, as this delay gets more and more, right, the frequency for which that filtering effect starts happening gets lower and lower. And sort of the depth of these combs, these change according to the value of G. So if G is, really small, I mean, which makes sense here. If G is 0, there's no reflected path. I just have the direct path of sound. But as soon as you have some sort of reflections, you have this. So what it tells me is that if I have a rigid surface that's really hard and I have a main reflection from that, that's going to cause a lot of this kind of comb filtering effect here. And I can listen to what that might sound like. So here I have, okay, so here's my input signal.
The Norsemen considered the rainbow as a bridge over which the gods passed from Earth to their home in the sky.
And what I'm going to show you is that, I can synthesize. All I'm doing here is I've built up those exact impulse responses, and this N and this G are changing how that impulse response behaves. So if I change N, you can see the magnitude response changes, and if I change G, the magnitude response changes. And I'm in real time, I'm sort of synthesizing, I'm doing the convolution with that new impulse response with the output. So you can end up getting something like,
The Norsemen considered the rainbow as a bridge over which the gods passed from Earth to their home in the sky.
And if you increase that delay quite a lot, you can hear it more as kind of a delay filtered type of effect.
The Norsemen considered the rainbow as a bridge over which the gods passed from Earth to their home in the sky.
Right. So that's sort of a basic, that's sort of our sort of first glimpse or first glance as to, what you can do with a feed-forward comb filter. And those are kind of some basic effects that you can get. And I'll just go to the last one, right, and quickly go through this one. So one limitation that you have with this feed-forward comb filter is that it only models one reflection. And remember, if we're designing virtual physical spaces, we need to design reflections from, coming from all over. And that gets really complicated, right? So how can we modify this feed-forward comb filter in the simplest way possible to model multiple reflections? Well, it actually is quite simple. Basically, what you do is you first delay the signal, and then in the output, you feed that back to the input here. And so that path that feeds back is multiplied by some gain G, and it's fed back into the input here. And this is what we call a feedback comb filter. Okay. And so you can see the structure is different, right? Whereas in the feed forward comb filter, you didn't have this type of recursive structure, but now in this feedback comb filter, you do. And again, we can go through the same sort of mechanics here. You can ask yourself, what's the difference equation? So the difference equation in this case is x of n minus n, because we're first delaying, and then we take that delay and we send it back to the input here. And we just simply multiply G multiplied by N minus capital N here. The impulse response, I was actually going to leave that as an exercise for you to sort of think about that and see how that makes sense. But I'll show you what that looks like. So this is an example of what an impulse response for this type of filter now looks like. So you now have a bunch of impulses that are delayed successively, and they're decreasing in amplitude here. So here's an example for N is equal to 200. I'm delaying by 200 samples, and G is equal to 0.9. And because of this recursive structure, what you do have now is this is in fact an impulse, infinite impulse response filter. And that's because of that feedback mechanism that you have going on. And you can ask yourself, well, first of all, I want you to, as a homework, to convince yourself that this is true by using those basic equations and looking at what the impulse response is to that system. But with this, we can ask ourselves the same exact questions, what is the output going to sound like to some input? And how is that going to change with delay N and G? And again, we make use of the same tools that we have. We have our difference equation. We can convert that to the Z transform. So right, I mean, these delays become Z to the minus N times X of Z, G times N to the minus N of Y of Z. And if we rearrange for the transfer function, now we actually see two components. We see a numerator component and a denominator component, which means that, right, this is now an IIR type filter here. So we have a set of delays on the top and this 1 minus G to the power of Z minus N. And we could also do a similar thing by looking at its frequency response by setting Z is equal to e to the j omega times TS. Okay. Just to take a quick look at this transfer function, and it looks fairly simple, but it's important to understand. So I can rewrite this, all right, just by multiplying out by z to the power of n here, and I can end up with this equation. There are a bunch of zeros when z to the power of n is equal to 0. And this gives you n zeros at z equals 0. And at the denominator, this has poles because the poles are when the denominator is the values of z for when the denominator is equal to 0. So I have z to the power of n minus g is equal to 0. So z to the power of n is equal to g. And so what this corresponds to is n poles that are equidistantly spaced around the unit circle. And each of those poles actually has a magnitude of g to the power of 1 over capital N here. And those are important because as you know, depending on where these poles are, you have problems with stability. And I'll show you what that looks like. And so the condition for stability is that the magnitude of this pole, of these poles, so the magnitude of G needs to always be less than 1. So you need to make sure that these poles are always inside the unit circle to make sure that the system is stable here. So let me show you this quickly in Python so you can see. So now I have this feedback filter comb structure here. And again, what I've done here is I've created I've now created coefficients for B and A because this has numerator and denominator values here in this. So if I look at this, okay, and I can see, so I can change here the value of N, and you can see as I change the value of N, this is what my impulse response is starting to look like. Right? I see this decaying set of impulses over time. And that's also having an impact again on the magnitude spectrum. So this magnitude spectrum has a bunch of resonant peaks all across frequency, and that's going to shape the sound in a particular way. And if I change the value of G here, I can say I can either make that, like have a lot of these peaks over time, or I can just have a few of them, and that has an impact on the frequency response. Now, as G tends to get to 1, right? You can see now things are slowly starting to maybe blow up a bit because now you have these samples that are remember, it's a feedback loop, so it keeps on repeating and repeating and repeating again, and that could cause some instabilities. And you can look here to these are. Let me get a better sort of value here. So these are what the poles of the system look like, and they're quite close to the unit circle, but they're still not fully outside, so they're still fairly stable. So you can play around with this and see, the impact that G has on these values, right? So yeah, it's starting to get unstable because they're closer to the unit circle. So you can see these are how the poles are distributed all over the system, and these are really important for the stability of our system. And so we can answer the question of, what does this all sound like as well too. And so done this here again. And so again, we have our same input signal.
The Norsemen considered the rainbow as a bridge over which the gods passed from Earth to their home in the sky.
And I can sort of start to change these values here of N and G, and you can see the output being generated. And so
The Norsemen considered the rainbow as a bridge over which the gods passed from Earth to their home in the sky.
starts to sound, it has a
The Norsemen considered the rainbow as a bridge over which the gods passed from Earth to their home in the
this
sky.
metallic-ish like sound. And actually you could see as I amplify G close to 1. So this is what we mean by instability, right? This is what the output looks like. And you can listen to it.
The Norsemen considered the
I like to break systems a lot. So this is, to me, this is really insightful because, now I understand, okay, that's what they mean when poles go outside the unit circle. That's what instability sounds like. And so that's quite instructive to me here. So I'd encourage you to kind of play around with this and kind of get a feel for the various changes and have a look at the code. I didn't go through too much details in the code because I didn't want to bore you too much with that. But if you have trouble with understanding it, just please, write me an email and let me know. Okay. So so that was sort of the main things that I wanted to talk about, just to kind of show you at least a bit of a link between some of the core concepts that you were all learning, and then how this manifests itself in the audio world. And this is only really the building blocks. Like I said, these are very simple models. I thought were simple enough to explain to you, but hopefully it makes a bit of sense, and you kind of get a better idea of how these things are practically used. And it's a starting point for more complex artificial reverberation if you're interested in that. Um, the final bit I just wanted to quickly mention is, if you're, try to give you a bit of a taste of what this all entails, and I hope I did that to some degree. But if you're really interested in more audio effects, they're really a lot more to look at. There are lots more, tons of resources to look at, even though that these models I show you remain as the building blocks for more complex artificial reverberation systems. One of the books that is really great is actually a book called Digital Audio Effects. So you can see if you can get a copy in the library. I'm not sure if the UE library has it, but if you get a copy of this, it's really a fantastic book. And it tells you, it goes a lot more in depth into various audio effects, how you use DSP to generate them, how you use DSP to manipulate them and do all these things. Some of you might have also come across notes from Julius Smith from Karma at Stanford. So he's done a lot of work on audio synthesis in general, and so he has several different online books, which is about mathematics of the DFT, introduction to filters, physical audio processing, spectral audio signal processing. And so if you really want to take a dive, I highly recommend this, and I think you all have the background knowledge to be able to comprehend that. Um, Another place you could look is there's an annual conference, which is called the Conference on Digital Audio Effects. And if you go to this website and you go to the previous you go to the conference proceedings, you'll see sort of what state of the art is, what people are working on, what are interesting things that is sort of hot and people find important as well too. And we're really familiar. If you want some more advice on this, let me know. We're really familiar with this community because in fact this was hosted here. We organized and hosted this last year at University of Surrey. So we're pretty well involved in that as well. Okay, I've left here a bunch of other references as well with various things. But I thought that I was only gonna speak to you for an hour, but of course I just keep blabbering along. But now I think I'll be quiet and if you have any questions, I hope that was helpful and I'm happy to answer any questions that you might have. Yeah.
Okay, so the floor is open. Feel free to ask the questions and so on. In the meanwhile, excellent presentation, Randall. Thank you very much for that. The thing about it is that everything that you spoke about, we've actually covered in class.
Good.
We did impulse response and so on some time ago, but the whole thing about the feed forward and feedback structures and so on, they did that quite recently. So it should they should be able to tie it back to everything that you spoke about here,
Cool. Sounds good.
right? There's a question there. Are the questions limited to the lecture? Not necessarily. You have someone here, Mika, so you could ask him or Micah.
Yeah. What type of standards? Ooh, okay, yeah. So there are various standards. One which comes up a bit, at least in terms of doing acoustic measurements. There's a standard called the ISO 3382, I think, and there are a bunch of standards for um how to make these sort of measurements for analyzing acoustic systems in general or doing reverberation measurements in a room and whatnot. There are another set of standards which are about doing perceptual testing. I'll have to look up exactly the names of those. I don't remember them offhand, but they're standards for stating what type of listening tests you should do, what types of rooms you should conduct listening tests in, because when people need to do perceptual evaluation of these things, usually what you do is you give them a bunch of sound samples and you need to come up with questions to ask them how to rate these certain things. And they're in a space and they're listening to the sounds, and that space needs to meet certain criteria, certain standards, and whatnot. So yeah. So experience or process for specializing. Um, yeah, well, that's a long question. That's a long answer to that question. Um, it was it was it was long and it took me a while to kind of get into that and to be able. I mean, I was interested in music and audio for a long time since my elect days. So for me, it was, just trying to get my hands on anything that I could do related to music and audio. So even like final year elect projects, I would always go for something in audio, and I always felt like I needed to go deeper and deeper. So it was challenging to find programs that specialize in that area and to go into that. But I mean, I was fortunate enough to find like good people along the way that kind of helped me along and helped me understand and yeah, I mean I think it takes time, it's not that these things they take a lot of time for it to kind of absorb and make sense of. Sometimes I even remember like I would have maybe 5-10 years later stuff from this course probably actually clicked and I was like, oh, that's what Fazil was talking about all the time. So, it takes time and you need to be patient with it, but just keep reading and looking for more practical examples. And recently I've found these sort of way of interacting with audio signals in Python in these notebooks. I found that so useful because, I could really practically sort of see, okay, that's what they mean when they do a digital discrete convolution with an audio signal, and that's what it sounds like. That's how I represent a signal. That's what, so I think these things really help as well too. Yeah.
Anyone else?
Um, what do you mean circumstances? You mean sort of in terms of equipment or in terms of feel free to pop on the mic and talk to elaborate on that. But do you mean like noise levels? Do you mean background noise levels? What are you thinking? Yes, no.
Hi, Verinda, are you asking the question or you typing on the question?
Typing maybe, I guess. Um, I mean, I could already say something perhaps about that. I mean, there are particular methods and standards for doing this. Of course, you need um, really quiet spaces to do this. So sometimes when we've done these measurements, we've had to do it at night when there was not a lot of noise in particular spaces. But then we actually ran into the problem that there are a lot of crickets and frogs making noise outside, and that also affected measurements too. So yeah, so ideally sort of a quiet room and good quality microphones and loudspeakers to do it. Okay, so here. The idea of recording sounds from a bedroom compared to professional studio. Yeah, I mean, that depends, right? It depends on the instrument that you're recording. It depends as well on the type of equipment that you have. But in terms of the space, one thing that affects smaller rooms like bedrooms are sort of dominant low frequency responses. So because you have, if you think of a sort of cuboid shaped room and there are small dimensions, you actually have what's called room resonances that are related to sort of the lengths of the room. So you can do a rough computation based on the speed of sound, and I think it's the speed of sound divided by twice the length of the room. And those dimensions, they support standing waves according to a particular frequency. And you have those standing waves which actually dominate a particular response, a particular part of the frequency range, and that might cause unwanted sort of coloration to your signals. Whereas, professional studios try to make the response of a room completely sort of flat and neutral, so that the room does not add too much coloration. But again, that depends. Some people might want rooms to add a bit of coloration, to be a bit live for, things like drum recordings, and others not. So yeah, so again, it really depends. But you have in general for smaller rooms, you have a problem with low frequency behavior that's sort of dominating the frequency spectrum.
Okay, anyone else?
Yep. Cool.
Yeah, all right. Well, okay, here we are. Yes, well, so somebody's kind of giving a positive.
Yeah, good. I'm glad that made sense. I mean, when I do these things too, even though some of them feel basic to me, I always like get a new insight, and exactly when I did this plot with the unit circle, I was like, yeah, okay, that's cool, and yeah, you have this sort of second connection. So yeah, I really encourage you to make use of these notebooks. I think they're really helpful to kind of get the concepts.
Yeah, so I think that's it at this point in time.
Yep.
Um,
Great.
Randall, thank you very, very much. It was very interesting. And I think if the students have been paying some sort of attention during the course, most of the material that they covered would allow them to answer to at least understand this your lecture very easily. It's
Exactly.
nice. I've uploaded the notebook, the zip file for that as well. So they're
Great.
free to experiment with that.
Yeah.
And those of them who may have some time afterwards, if they're still here, going on to next year and so on, they can explore that and see what else is possible
Yeah.
and get in contact with you and well through
Yeah.
me or through whoever else is there
Yeah.
to,
My
to
email
further
is on the
anything.
slide. Mhm. My
Yeah.
email is on the first slide. So
Yeah.
anyone is welcome to shoot me an email. I'm more than happy to chat
Right, and
about.
if any of them are sort of now like next year now thinking about doing well what they would want to do in 3020 and would want to do something in this area and so on.
Yeah.
Well, now is a good time to sort of make use of the fact that we have the arrangement, we have
Yeah.
you available, and that we could
Absolutely.
work out some sort of arrangement for
Absolutely. No problem.
a project and some sort of joint supervision on it.
No problem at all. Yeah, that sounds fantastic.
All right. Okay,
Cool.
so let me stop
Great.
the recording now.